Welcome to Program Analysis Corner.
Hello, and welcome to this video where we will be covering a tool called SymCC that was presented at an academic conference this year called Usenix Security Symposium. And this paper, it was awarded the Distinguished Paper Award, which means that it is of very high quality and has some very interesting aspects to it. So what this SymCC tool does, which is what the paper presents, is that it essentially integrates symbolic execution by way of compilation rather than interpretation. And if we look at the paper, we can go down and look at the abstract here. And we can see that the authors write, we present SymCC, an LLVM-based C and C++ compiler that builds concolic execution right into the binary. It can be used by software developers as drop-in replacement for Clang and Clang++, and we show how to add support for other languages with little effort. So what this means is that SymCC is essentially integrated into the LLVM framework, and thus it can be used as a C and C++ compiler, and the concolic execution is integrated into the binaries that you compile. And after this little these few sentences, we see also that the authors write, in comparison with CLE, which is a symbolic execution tool that we studied previously in the channel, SymCC is faster by up to 3 orders of magnitude and an average factor of 12. It also outperforms QSym, a system that recently showed great performance improvements over other implementations, by up to 2 orders of magnitude and an average factor of 10. So this means one of the main arguments for having this SymCC tool is that it is much faster than the existing solutions, CLE and QSym, to perform concolic execution. So the main argument of these authors is that we can achieve symbolic execution much faster if we compile it into our binary rather than interpreting it. And they also perform some empirical evaluation and that shows their results. Okay, so what I will do in this video is I will essentially just get the tool from GitHub, try and install it, try and run it, and then see how it is. The way I would like to do this is I would like to install it by way of its Docker image, because they have a very they have a Docker image that does all of the installation aspects very nicely, and it makes it super easy to actually get started with SymCC. So what we're going to do is we will copy the link, and then we are going to clone the repository into our directory here on the left. If we do like this, maybe that's a little bit too much zoomed in. Okay, so now we have the SymCC source code here, and we will move into the folder, and then we are simply going to run these commands in order to build the Docker image of SymCC, and then also launch a shell inside of SymCC. So we simply run this command, then we run this command, and then after that we will build the Docker image using the docker build command. Okay, and now let's run Docker here as follows, and this will take a while, so I will just skip this in the video. Okay, so the Docker installation just finished, and now we're going to start a shell inside of this Docker image. Okay, and we are now inside of the SymCC Docker image. What we're going to do now is we are going to simply run SymCC on this sample.cpp file. But before we actually do that, I would like to just install a few more packages in the Docker image. So we're going to install, first we're going to just update here. That looks good. And then we're going to install the following packages, and we're going to install Vim less and also BSD main utils, and we want this one because I would like to have hexdump, the hexdump tool, and also I would like to have vim in order to view the source code of files. So this is being installed now, and then we are going to look at the sample.cpp, which is this file that is also inside of our Docker image. So let's look at the sample.cpp, and we can see that it is simply a C++ file that has a main function. It asks for what is your name, and then it declares a local variable, which is a local variable called name, which is simply a string. And then it takes input from standard in and puts it into the name variable. Afterwards, it does a conditional check on the name to see if it is equal to root, and if it is, it prints out something, and if it is not, it prints out something else, and then it returns. So the main point of this little test application is to essentially demonstrate that SymCC can accurately determine that there are a path here where you need to have root as the input to the application in order to trigger this path. Okay, so in order to compile this, what we essentially have to do is use the well, we have here the SymCC, but we need to use Sym++. But we need to use the Sym++, as you see right here, the Sym++ script, which compiles our sample.cpp. So if we go into the Docker image and we ask, what is this? We can see that the Sym++ file exists right here. So if we look at what it actually is, we can see that it is simply a shell script. And if we look at the shell script, we can see that if we go down, we can see that it is simply a wrapper around the compiler. And in this case, the compiler is set to be clang++, as you see right here. And so the way SymCC uses this Sym++ script, it essentially just wraps around the clang++ compiler, and then we use this loading of the LLVM pass. In this case, pass is simply given here, which lib_symbolize.so, and then this lib_symbolize.so file is actually the code the code of SymCC, which represents this LLVM pass that essentially integrates symbolic execution into the binary. So although we use this wrapper, Sym++, it is in fact just a wrapper around clang++, where we load this given LLVM pass, which also shows how simple it actually is to integrate into your tool chain, your compiler chain, because the only thing you have to do is load this LLVM pass during the compilation stages, which you can do very easily. Okay, so let's execute the command as shown in the documentation. We are here building a Docker image, and we are now down here. So we're going to use Sym++ on our sample input. Okay, so this is now compiled, and we can see that we have a binary here, which is really just a normal binary 64-bit L file. Okay, so what we will do now is we are going to echo some output and pipe it into our sample application. And the reason for this is that SymCC will treat all input from standard in as symbolic. So this is really the way in order to inject symbolic memory into our compiled executable. So let's simply go echo test and then sample and see what happens. And we can see now that a bunch of SMT, so SMT solver output came out, and we can see that it has generated various test cases here. And these test cases are placed in a tmp out folder, tmp/output, and it didn't take too long. So let's see what exists in this tmp output folder. And we can see that there is just about 9 files. And if we look at the content of each of these files, can see that there is some ASCII characters here, but instead I would actually like to see what the actual bytes are of these files. And to do that, I have a small command here, which can be very easy, which can be very convenient. So what we can simply do here is we can use the find command in temp output, and we then look for each file in this directory, and we print the name of the file as well as do a hex dump of the file. And the main point here is that we actually want to see the actual bytes rather than just the ASCII characters that cat gives us. So let's execute this, and then we can see we have all the files listed here together with the bytes and the ASCII characters of the file. And we can see here that in output 8 optimistic, we get this root input. So indeed, the SymCC was able to find the correct input that triggered this path to be executed. Okay. So how does SymCC actually work? And to do that, I have another example that I would like to go through. So if we copy this sample, and we will simply call it sample2.cpp. If we copy this into our Docker image, we can see that we have a main file here, and it is very similar to the other sample C++ file, where we have a first print here that asks us for the name, and then we take from standard input into this name variable, but this time we call into this nested checking function using the C string of the input. And inside of this nested checking, we get all of these conditional statements that essentially just checks the first character of the array, and then checks the second character, and then it checks the third character, and also the fourth character down here. And because SymCC compiles symbolic execution into the binary, what happens is that the binary executes as it normally would, but SymCC has added some extra code into the binary that performs symbolic execution of the path that is running inside of the binary. So say, for example, we are to execute this function, nested checking, in SymCC, and the input that we give is just all B's. Then SymCC, the compiled version of this binary, will read the input, and because it's all BBBs, it will call into this function with an array purely of B's. When SymCC reaches this conditional statement, the instrumentation that SymCC has added to the binary will analyze whether this condition is satisfiable in case the input was symbolic. And if it is, it will then get the input that says, okay, actually the first letter of the input needs to be an uppercase A. But because it actually executes concretely, it will not try and execute anything in here, because all the B's in our concrete path is simply going to reject this conditional and then return down here. And what this means is that we have to execute the binary over and over again using the various inputs generated from SymCC. So for example, in the case where we give all B's, SymCC will tell us that if we actually give an uppercase A in the first, as the first character in the input, we will trigger this condition, and then it will give us the input that satisfies such that execution will go into this conditional. And then when we execute that given input, it will execute concretely, but because most likely the input will not have an uppercase B in the second position of the input, it will again, because it executes concretely, it will again reject this condition, but the instrumentation of SymCC will calculate that this path is possible if we give an uppercase character on the second position, and the same will happen down here. So where it will find that this second path is satisfiable, or this path is satisfiable if the second character is an uppercase C. But the concrete version that has an uppercase A and random garbage on the rest of the characters will not go into any of these conditionals and thus exit shortly afterwards. So the point is we have to execute over and over again with some random input, and then afterwards we have to execute the same binary, but with the input, with the output, which is now input, generated by SymCC. And this is really a consequence of SymCC compiling the symbolic execution into the binary. Okay, and just to clarify that this is different than to for example, to CLE, which would explore the entire of this function in sort of like one execution. Okay, so let's now actually try and compile this and execute it and see a little bit more how the behavior of SymCC is with this nested checking. Okay, so we're going to compile it in the same way. Sym++, and let's just do sample2 and sample2.cpp, and we have that here now. And then we will just clean the output directory where the files are stored, and let's just make the output directory again. And what we're going to do now is we are simply going to add, say, echo a lot of else into the sample2, and we need to pipe it in. Okay, so what happened in this case is when we give a lot of else, uppercase else as input here, then essentially what simply will happen is that this conditional will fail. But we will be able to find one of the test cases to have a uppercase A that will show us how to get past this conditional statement. Okay, so let's look at the output directory here, and let's just look at what this file has. I think that's the one that has the content. And indeed, that input generated by SymCC actually has an uppercase an uppercase A. And this means that SymCC was indeed able to find the input that triggers this execution to be true. So if now we actually try and take that input and pass it into, let's actually also just see and verify there's no inputs with, say, for example, a B in the second position or an M in the third position within our within the test cases generated by SymCC. And the goal is here simply to verify it didn't find the second conditions. Sorry. And you can see here that we have the uppercase A, but we don't have any test case that includes the uppercase B in the second position. So what we do now is we're going to, let's remove this folder again. And then we're going to now include an uppercase A in the first position of the input. And then let's just give a lot of else here, and then pipe it again to our sample2. And the main point is here, now we are going to, now SymCC is going to find out that there is actually the opportunity with this input, having an uppercase B in the second position of the input will trigger a new path. So we're going to execute this, and we can again look at the content of the files in the TMP output folder, and we can see that there is indeed one with an uppercase C here, and there's also one with an uppercase B. And if we look at sample2.cpp, we can see that if the first character here has an uppercase A, which it does in the concrete execution, it will find out that if we actually get a uppercase B in the second character, in the second position of the input, it will trigger a new path. and also if we get an uppercase C in this case. So here we can see that SymCC is able to generate multiple inputs based on a single concrete execution, which indeed is what we just saw, because we got two test cases where we both had an uppercase B and an uppercase C. Okay, in order to solve this problem of continuously passing in the input generated by SymCC, or the output written by SymCC that can contain new input, the SymCC authors have included a script. And this script is accessible here, called pure concolic execution. And this script is accessible inside the Docker image under the SymCC_build, and then pure concolic execution. And essentially what this script will do is that it will take the output of SymCC and then pass it into the application again, and it will then do a bit of hashing on all of the inputs in order to remove duplicates. So let's just try that script, and the way we're going to do it is we will have an input directory, we will have an output directory, and then we're going to do SymCC_build pure concolic execution, and we're going to say the input directory. Actually, first we have to just create a seed in the input directory, and the way we're going to do that is we will simply have a file here that we are just going to output into the input directory, and we call it seed1. And then we can now call this script where we say input is the input directory here, and output is the output directory. And then we have that the binary we are going to do it on is the sample2 binary here, which is our binary with symbolic execution or concolic execution. And what this script will do is essentially just execute it over and over again. SymCC. We can just take a look at the script, and perhaps the most important one here is that we go through the generations. So say run generation after generation until we don't generate new inputs anymore. So it will just continue to generate new inputs based on the inputs we just generated, and the first input we will start with is the seed1. So if we execute that, we can now see that it first runs our seed, and because the execution with this seed generated a set of new paths, then this will then be input back into the application, and we can see that we will continue to get further generations, and it really just goes on as of now. And the reason that we see all of these different inputs, it's not that each input actually executes a new path in the system. It is really in the program that we're targeting. It is really that each of these inputs just has a unique hash sum in comparison to the other inputs. And because the SMT solvers will generate random input, we can have many inputs that actually execute the same path. But let's now look at the output, and we can see that SymCC actually generated 1,800 different seeds. And if we just look at a little bit at those, we can see that did it find a seed where it first had an uppercase A, then an uppercase B, and then an uppercase M. Let's see if we found that a seed that had this content. So we're simply going to do grep for ABM inside of the out directory, and we can see that indeed we actually did get a seed with these characters. And we will also have all of the other characters such as A, C, D, E. So let's do A, C, D, E. I think that was the one, and we want it to be recursive. Maybe I was wrong. Oh. A, C, D. Okay, so we got to A, C, D, which is right here. And the reason we didn't get to the A, C, D, E is because we only got to, say, generation number 3. So if we just see if we can catch this in the output, it actually weren't there. So instead what we're going to do now is let's just clean the output folder, create a new one, and then we're going to execute it now. And we're going to write all of the output to a file that we simply call SymCC output. And let's now see how long it takes to actually get to this ACDE input, which should be in generation number 4. And I will just run it for, say, 30 seconds and then restart the video. Okay, so we now ran it for a while, and let's see how many files we generated. So now we generated 2,100 seeds, and let's now grep for generation, because it will tell us which how many generations it achieved. And it's in SymCC output, and we actually only came to generation 3. So let's see if we have a file. We don't. Let me just try and execute it again. And now I will execute it for, let's say, 2 minutes, just to see and verify that we actually can get the 4 characters. So we will execute it again, and this time to SymCC output 2, and then we're just going to execute it for a much longer time, so we can ensure that we actually get to generate generation 4, which will then be make it possible for us to reach this statement where we have both A, C, D, and E, and also in that, when that happens, we will also have F. Okay, so I now executed it for a bit longer, and let's see how many inputs we actually generated. And we can see there's now 5,600. So let's grep for generation in SymCC output 2. And we see that there's still the 3rd generation. I'm not going to do this again because we already have it, but we can certainly tell that now we have explored sort of a depth of 3, but we didn't reach the depth of 4 just yet. However, SymCC will be able to do this, and the reason we don't get to this depth 4 is that, or let's put it differently, the reason that SymCC actually generates so many inputs is not because each of these inputs execute different paths. It is really just that, so like this script, say pure concolic execution, simply just removes duplicates by looking at the hash sum of each of the inputs. So I think perhaps it's here, copy with unique name, where we check the hash sum of the input, and because of the way SMT solvers work, we will have a lot of different inputs that actually trigger the same execution paths. But the execution speed of SymCC is very high in the sense that it the way calculates the path conditions is very fast. But because we don't really have a nice way at the moment to remove duplicates in terms of duplicates that trigger the same path execution, at least not using this script, we will generate a lot of duplicates in terms of inputs that execute the same path in the program. Okay, so I will leave this for now as an introduction, and I will maybe make a new video going into a little bit more going into how you can use SymCC with a little bit more advanced examples and more real-world software. But I will leave this for now. I hope you enjoyed it. Thank you.